Hello, everyone, and welcome to the 20th Sports Media Tea Time Talks webinar. My name is Mohammed, and I am your host today. Also accompanying me in the studio, we have Marcel Moura from University of Oslo, Nara Brandao from Federal University of Uberlandia, and Javier Santos from University of Texas at Austin. Porous Media Tea Time Talks is a platform for young and early career researchers to present their work to broader scientific community around the world. The Porous Media TTT's goal is to act as complementary platform to the already very successful geoscience and geoenergy webinars, which is organized by Hadi and Sebastian. Now let's introduce our first speaker. Today's first presentation is by Maxime van der Heijden. In 2019, she started as a PhD student at the Eindhoven University of Technology in the Membrane Materials and Processing Group from the Department of Chemical Engineering and Chemistry. The aim of her research is to design and synthesize novel electrodes with architected microstructures by using a combination of computer simulations and synthetic methods. Today, she's going to talk about bottom-up design for porous electrode microstructures for redox flow batteries. I like to mention that everyone who wants to ask a question can type it in the comment section during the presentations. With that, I would like to thank Maxime for joining us today, and the floor is yours.
Thank you very much for your kind introduction and for inviting me today. I will briefly walk through my PhD project where I try to design porous electrode microstructures for redox flow batteries from the bottom up and show my progress of the last 1.5 years. So energy has become a very important aspect in our daily lives, but it's still primarily generated by fossil fuels. Fortunately, the transition to a circular economy by integrating renewable energy is a hot topic in research and is expected to increase tremendously in the coming years. Because renewables are intermittent in nature, the demand of energy does not meet the supply of solar and wind energy. Therefore, techniques must be developed to store the electricity on a large scale to always provide the grid with electricity. One possible technique is by storing electrical energy into chemical energy in, for example, redox flow batteries. So a redox flow battery is a gigantic type of battery that stores energy in liquid electrolytes kept in big tanks, where the electrolyte is pumped through the reactor to convert electrical energy into chemical energy and vice versa. The main advantage of redox flow batteries for energy storage is that upscaling possibilities are possible, making them a suitable candidate to store electricity at a large scale, as energy and power can be independently scaled depending on their application. The major drawback of redox flow batteries is, however, that they are currently too expensive. This is because they are not optimized yet, resulting in efficiency losses. In my research, I will focus on improving the porous electrode in redox flow batteries, as they are responsible for electrochemical reactions that take place at the porous electrode surface. Some of the main properties for a good porous electrode are a high surface area, a low pressure drop, and good mass transport through the electrode. However, some of these requirements are contradictory. Previous research on porous electrodes showed the importance of hierarchical organization of the microstructure. It showed that high hierarchical organization strongly improved the performance in terms of power output and pressure drop, which are translated to the overall cost of the system. However, currently used electrodes are developed for fuel cell applications and not for all liquid systems, and this results in significant power losses in the battery, which can be split in activation, ohmic, and mass transport losses. Therefore, it is important to improve existing porous electrodes or fabricate new electrodes for this specific application. In my research, I will therefore try to fundamentally understand the relations and importance of the electrode microstructure to fabricate optimized electrodes for redox flow batteries. The starting point is the experimental characterization of commercial electrodes to understand the importance of the electrode microstructure and find important relationships. Additionally, experiments will be used to validate the models that eventually need to predict the optimized microstructure. The next step is creating a Pornef model, which can model and predict the performance of your battery. Using this model, a genetic algorithm can be created based on the evolutionary theory of Charles Darwin to predict optimized microstructures from the bottom up. When these structures are generated, we go back to the lab and manufacture and evaluate these electrodes to see if the performance is indeed improved. But first, a model must be built. So many different types of models exist, all with their advantages and flaws. For example, in macroscopic continuum models, you can model the overall performance of your system very fast, but you need a lot of assumptions and you don't have information about the pore scale of your electrode. On the other hand, models like lattice-Boltzmann models are very complex and provide detailed information about the reactions in the pores of the electrode, but fail to capture the overall performance of your battery. Therefore, we choose to use a pore network model, which can capture the performance of your entire system, but also gives you important information about your electrode structure, exploring the right design space with a computationally inexpensive and versatile model, which is perfect for the approach of this project. Using an iterative algorithm, the performance of the system can be modeled, where the foundation of the model is based on 3 transport mechanisms. The first one is fluid transport, where in the experiments and model, the fluid is pushed through the electrode from the bottom to the top. The second one is the charge transport. The experiments were performed for symmetric batteries because you will not see the effect of, for example, electrolyte crossover through the membrane. This results in that the same but reversed reactions are occurring in the Hall cells. And finally, the species transport, which is strongly coupled to the charge transport. The advantage of a pore network model is that a real electrode can be used to model the transport in the battery. This electrode can be extracted using X-ray tomography, and subsequently the porous network can be obtained with the so-called Snow algorithm, which can be used in the model. And this work, I modeled the performance of a non-woven and a woven electrode. And to make our lives a bit easier, an open source software package was used called OpenPNM to model the pore network, where the pores and throats are translated to spheres and cylinders. So this PNM was validated for 2 different chemistries by using an organic and an aqueous electrolyte and 2 different commercial electrodes. So a non-woven and a woven fibrous electrode. The organic electrolyte is perfect to validate the model as it wets the porous electrode perfectly, which is assumed by the model. These graphs show a polarization curve, which shows the performance of the system by plotting the applied potential at the y-axis and the current density at the x-axis. In this graph, I plotted the experimental data and symbols and the model as a line, and I plotted the performance for 3 different velocities. So when analyzing the performance of this electrolyte for both the non-woven and the woven electrode, you can see that the model fits the experimental data very well. This validation was done without the use of fitting parameters, besides the determination of the exchange current density from experimental data. When analyzing the validation for an aqueous electrolyte, it can be observed that the model does not match the experimental data very well. This is a result of the incomplete wetting of the porous carbon electrode. And to try to capture this effect, the mass transfer coefficient can be fitted, capturing the model's behavior fairly well and validating this model additionally for aqueous electrolytes. So using the validated pore network model, we construct a genetic algorithm based on the evolution theory of Charles Darwin that can create optimized electrode structures from the bottom up, dependent on the electrolyte's chemistry. So in a genetic algorithm, you start with many parameters that will create a number of individuals, defining your first generation. You will evaluate the performance of these individuals with the aforementioned pore network model to select the best or fittest individuals. This selection is based on the performance of the networks with a fitness function, based on the overpotential and the pumping power losses, and achieving a fitness function closer to 1 results in individuals with a better performance. Then the next step, the best individuals, the parents, they can mate to form new individuals. And these new individuals then have a chance to be mutated before they form a new generation of individuals. Then this generation is again evaluated and this process is repeated until a maximum amount of generations is achieved. So we are still in the starting phase of developing this algorithm, but I can already show you some initial results. I evaluated 50 individuals, 10 parents, and I let it generate for 1,000 times. And I did it for a small semi-2D cubic network to increase the speed of the algorithm. So when analyzing the fitness evolution, you see that each generation, the fitness improved. This means that the approach actually worked. When looking at the polarization curve, you can see that the performance significantly increased between the first and the last generation. It must be noted that because the porosity is very low, to give the GA more degrees of evolutionary freedom, the fitness and the current density are very low, and they are not a real representation of a commercial electrode. So when analyzing the increase in performance, we showed that we observed a 53% increase for the generated power and a 90% decrease for the pumping power. And this is really significant, and it shows that the genetic algorithm, or GA, can optimize both the pumping power losses and electrical power. So now let's evaluate what happened to the network structure. In the first generation, the pores, shown here, are random and with a straightforward pore size distribution. In the last generation, on the other hand, the structure evolved by creating many big pores and small pores where the porosity was kept constant. This structure showed shows highways of big pores in the flow direction, which improved the transport of the electrolyte and it decreased the pumping power. As the surface area remains about constant, the electrochemical performance is improved by the organizations of the pores itself. And as you can see in the pore size distribution, which changed significantly, a bimodal pore size distribution is observed for the last generation, which was also observed for the woven electrode structure I mentioned before. So to conclude, this genetic algorithm showed that it's able to optimize a random cubic network by optimizing for the pumping power losses and the electrochemical performance, and showed the importance of hierarchical organization of porous electrodes. So I showed the proof of concept for the genetic algorithm, but we are not close to generating perfect electrode microstructures for redox flow batteries yet, as we need to incorporate more design operators to explore the broad design space of the electrode to generate more realistic networks. Additionally, manufacturing constraints need to be considered as we model a pore network and not a solid structure that you eventually manufacture. Even though we are not at the point of generating a perfect electrode yet, we already need to look into the future steps, so the manufacturing of the electrodes and eventually device implementation, which will be the future steps of my PhD. So of course I had help during my PhD, and therefore I'd like to thank the following people for the contributions. So Rick, Gabor, Tony, Sandri, Amin, Jeff, the MMP members, and NWO for funding our research.
All right, so thank you very much, Maxime. The floor is open for questions. So if there are any questions from the audience, please do type it in the comments on the right of your screen. I have a couple myself. So this genetic optimization method that you say, this is an outcome of your work, right? This is not something that is already in the literature, right?
Yeah, so there is no literature that we know of a genetic algorithm for to optimize electrodes for redox flow batteries yet.
Right. So what I was wondering is this something that can be used generally? Like once it's developed, is this of a general use for, say, for pore network modeling for other kinds of problems, or is this something specific for the applications that you are working on here?
I think the algorithm itself can be used for everything pore network based, but we use the pore network model with the algorithms that are specific for liquid-liquid systems like in redox flow batteries. But if you adjust only that model, you can basically optimize all structures based on spheres and trodes, I think.
Right. Oh, that's very nice. That opens up for many other possibilities for applications of that, I think.
Yeah.
Also, you mentioned your model is wetting to the liquids, is that right? Is this something that can be tunable, or is it like necessarily wetting, necessarily completely wetting?
I think it's possible to include non-ideal wetting behavior, but because it's very difficult to actually evaluate which parts wet in the electrodes and which part not, we first need to investigate that better before we can include something in the model.
Right. I see.
But that's
Thank
also
you.
a part where I'm really interested in figuring out how that works, because most batteries are aqueous, use aqueous electrolytes. So it's really important, actually.
Mm. All right, so are there other questions? Let's see. We also welcome the audience to contact directly the speakers if they have any questions at any time.
Oh yeah, wait,
So,
I added my email here.
yeah, there it is.
Yeah.
So now you have Maxime's email and you can contact her anytime with further questions.
Yes.
So thank you very much. I think we can move on to our second talk for today. And this one, we got a pre-recorded version of the talk, so we'll be streaming it for you.
So much for tuning me in. First of all, I would like to thank the
right there. So if you have any questions, you can we'll try to make our questions and answers sessions at the end of the session. But if you have any questions, you can also send them directly to the speaker. And if you type them in on the right, we will also transmit those questions to the speakers for you. So now we move on with the streaming. Can you have it play?
Hello everyone. Yeah. Thank you so much for tuning me in. First of all, I would like to thank the organizer and Porous Media Tea Time Talk committee members for providing me with this opportunity to present my work on this great platform. Today I will talk about solid fluid interfacial area measurement for reservoir scale wettability quantification in porous media. As this topic suggests that I will be going to discuss a way to measure fluid solid contact area that can predict the reservoir scale wettability. So my question is with the audience would be that what is reservoir scale wettability? So before going to discuss about the reservoir scale wettability, I would like to tell what is wettability.
In general, wettability is defined as the ability of a fluid to adhere to a solid surface. If the fluid is more wetting for a surface, it will try to occupy more surface on the solid. And if the same volume of the fluid is non-wetting for a surface, then it will occupy less surface on the solid. So next question that comes in our mind, that how do we quantify wettability? So there are various methods have been proposed and already being used to quantify the surface wettability. And historically, contact angle method is the most frequently used method to quantify the surface wettability. And many research with microcity analysis has proved that the contact angle method can be applied in a reservoir pore to quantify wettability. But we are interested to know the reservoir scale wettability. As we know that reservoirs are huge, and when we talk about the huge geological system where we want to recover oil, and when we talk about the groundwater remediation where we remove the pollutants and want to recover harmless products, then in these kind of systems wettability play a very significant role. And when we go inside the reservoir, we see grains, and these grains can be water wet, mixed wet and oil wet. In water wet condition, water spreads or coat the grain surface and oil balls up and run off the surface. Vice versa in the oil wet reservoir, and mixed condition we observe in mixed wet reservoir. So in the oil reservoirs, wettability is a crucial parameter for the sediments, and it affects many other parameters that leading to varied oil recoveries in different wetting conditions that we have seen in our lab experiments and in many literatures as well. And also we know that there are so much heterogeneity inside the reservoir because of the roughness, because of the presence of the chemicals and multiple fluid flow inside the reservoir. Then how do we define the reservoir scale wettability? By just quantifying
First of all, I would like to thank the organizer and Porous Media Tea Time.
Spreads or coat the grain surface and oil balls up and run off the surface. Vice versa in the oil wet reservoir, and mixed condition we observe in mixed wet reservoir. So in the oil reservoirs, wettability is a crucial parameter for the sediments, and it affects many other parameters that leading to varied oil recoveries in different wetting conditions that we have seen in our lab experiments and in many literatures as well. And also we know that there are so much heterogeneity inside the reservoir because of the roughness, because of the presence of the chemicals and multiple fluid flow inside the reservoir. Then how do we define the reservoir scale wettability? By just quantifying the contact angle made by a drop on a flat surface. Then this was the most challenging and confusing question with which we deal. And recently we have studied that the X-ray microsity based approaches have shown that the fluid to solid contact area measurement can discriminate the different wetting conditions more efficiently than the contact angle method. Therefore, by recognizing that more wetting fluid has more interfacial area with the porous solid, we can say that we can predict the reservoir scale wettability by just measuring the fluid solid contact area. So now we set out to find a way to discover reservoir scale wettability by just measuring the fluid solid interfacial area, and for that we will talk about it. So for measuring the fluid solid interfacial area at reservoir scale wettability quantification, we have explored the dual tracer method that was used to characterize the catalyst in a liquid solid gas system. In our methodology, we performed steady state single and two phase flow in a cylindrical porous medium as a proxy for the reservoir, with the inlet as the injection well and outlet as the producer well. We used two tracers for a fluid phase, an ideal tracer and an adsorbing tracer. If we are using one ideal tracer here because the ideal tracer will follow the flow path and tells us about the void volume available inside the porous medium. And we use adsorbing tracer because adsorbing tracer will dynamically adsorb and desorbs on the solid surface and shows a certain delay to arrive at the production point. And we know that the adsorption and desorption is the surface phenomena. Therefore, based on the delay, we can find out the fluid solid interfacial area using this equation. In this equation, there is two unknown, that is Ka and Ai, where Ka is the adsorption partition coefficient on the solid metric and Ai is the fluid solid interfacial area. So using this equation, we can measure the fluid solid interfacial area, that is Ai, only if the Ka is known to us. Therefore, our first task is to estimate the adsorption partition coefficient value for the fluid solid interfacial area measurement. So to estimate the Ka, we perform the single phase flow experiment at 4 different flow rates in a cylindrical tube which is densely packed with the glass beads as our proxy porous medium. During the single phase flow, at the steady state, we first inject the ideal tracer as the step input and then we inject the adsorbing tracer at the same condition and same flow rate. And then we get slight delay in adsorbing tracer breakthrough curve. And this breakthrough curve tells us the mean residence time of the tracer inside the porous medium. And identically, we know that the first moment of the tracer should be equal to the theoretically mean residence time. Therefore, first we compare the experimentally calculated mean residence time with the theoretically mean residence time. And at 4 different flow rates, we see the ideal tracer mean residence time has an excellent match with the theoretical mean residence time as it is expected in our equation. And at the same flow rate, we get the higher mean residence time of the adsorbing tracer, which is also expected due to the tracer adsorption and desorption on the glass bead surface. Then the difference in MRT gives us Ka AI divided by Q, where Q is the flow rate and Ka is the adsorption partition coefficient and AI is the fluid solid interfacial area. And because we know AI during the single phase flow, which is equal to the whole solid surface area of the porous medium, because in single phase flow the whole solid surface area of the porous medium is being covered by the single fluid only. Now the estimated Ka at 4 different flow rate for water tracer flow experiment we have shown here, and by this result we obtain that the calculated adsorption partition coefficient value is independent of the flow rate, and which validate our assumption of the linear adsorption isotherm as well. And we calculated Ka for the aqueous phase tracer is 0.03 ml per gram, and for the organic phase tracer we calculated 0.05 ml per gram. So next we use this estimated Ka in 2-phase flow experiment to measure the fluid solid contact area. So to measure the fluid solid interfacial area at different residual phase saturation, using the estimated Ka during the 2-phase flow experiment, I am showing here an experimentally obtained tracer breakthrough during the 2-phase flow. And when we compare the 2-phase flow curve with the single phase flow curves, then we obtained early arrival of the tracers during the 2-phase flow experiment. This is because the volume occupied by the mobile phase is reduced in 2-phase flow due to the presence of the remaining, or we can say the residual phase. So the difference in tracer breakthrough curve, or this gap, or we can say delay in this tracer breakthrough curve during the 2-phase and the single phase is actually tells us about the volume occupied by the residual phase in the 2-phase flow system. And this residual phase volume we can also measure by the mass balance analysis, and we obtain an excellent match in our lab experiments. So by knowing the volume fraction of the residual fluid, we can calculate the saturations of the liquid during the 2-phase flow. So now if we use only the 2-phase flow curves, then we can measure the fluid solid interfacial area during the 2-phase flow using the estimated Ka at different saturations. So here I am showing the fractional water weighted surface area of the glass beads at different water saturations. When the circle shows drainage, when water is the residual phase and oil is the mobile phase, and the square shows the imbibition curve when the oil is the residual phase and water is the mobile phase in the porous medium. So by this curve we observe a monotonic and a non-linear relationship between the interfacial area with saturation. So further we can look at the data in another way, that the drainage curve is higher than the imbibition curve for the same saturation. So this result shows that when water is at the residual saturation, it has more interfacial area with the porous solid in compared to when oil is at the residual saturation. And further, we performed two-phase flow experiments when both phases are simultaneously flowing into the porous medium at different wetting conditions. In this situation, we also obtained the same monotonic behavior of the interfacial area with fractional water flow rate during the different wetting conditions. And this work is remain tuned in for our next publication. So, in summary, we demonstrated the use of the dual tracer method for direct measurement of the fluid solid interfacial area during the multi-phase flow in a porous medium. To prove the concept, laboratory experiments are designed as a two-step process. First, single-phase flow experiments we perform to find the adsorption coefficient value, and second, two-phase flow experiments are performed to find the fluid solid interfacial area during the multiple fluid flow in a porous medium. And we observed that the contact area has a monotonic behavior with the saturation during the multi-phase flow. And our methodology can be used to estimate the fluid solid interfacial area at different wetting conditions and in flowing conditions as well. And next, we are working to investigate the solid liquid interfacial area at different wetting conditions and different saturations.
So thank you for your kind attention, and I would like to acknowledge my supervisor Dr. Jyoti Firani and my research committee members and IIT Delhi funding agency collaborators, and lastly my family and friends. Thank you so much once again.
Okay, right. Thanks, Deepshikha, for sending to us your recorded presentation. And I encourage the audience to type your comments here on the chat, and then we can share with Deepshikha because she's online with us. And we are receiving positive feedbacks for you that I'd like to share with you. The first one is from Martin Blanc. To very interesting presentation. I'd like to use the tracer to measure the interfacial areas. A good complement to direct imaging. And also a good feedback from Sunil. It's a great talk on wettability quantification. And we got one question, Deepshikha. So please, I just want to make sure, can you hear me? I guess so. Let's just... Okay, I guess she's mute. And so please, Deepshikha, I guess you are mute. Okay, let me just... Okay, so I guess we are having some internet connections, some issues, but I can share with you that Sunil is asking, but I want to know its theoretical implication in short. So please, Sunil, I will say to you that Deepshikha, will answer you by email. I guess we are having some internet issues connection from her side, so we apologize for that, but make sure that we are gonna answer you through email. Okay, Deepshikha? Yes, we can answer you by email. Thank you very much for your participation. And so I guess we can move forward, and then I'd like to share with you our next presentation. We are happy to have a special section for a national chapter from Interpol from Norway. We are gonna have How and Santana that will talk, and how we will talk about numerical modeling of fracture deformation and propagation in pore-elastic media. And Santana will talk about disorder and non-linearity in two-phase flow in porous media. It will be on 18th of June at 3 p.m. CEST. And today we also want to share with you some news that we are very happy and proud, and for that I will invite Marcel.
All right, thank you very much, Nara and everyone. Thanks for the speakers. I apologize a little bit for the minor technical difficulties that we have along the way. You know, we are all early career scientists trying to be YouTubers here, so I hope it's forgivable. So you see, like the more attentive there have seen that there is a new logo on our slide, and that's the Interpor Young Academy. So we are very happy. You know, in this first year of the Tea Time Talks, we had I think almost 40 speakers, and it's been very nice. And all along the way, we had the support of Interpor to advertise and give us like a very many good feedback on the whole activity. And now we are joining formally the team of the Interpor Academy, which is it's a new umbrella term within the Interpor organization to gather everything related to education on Interpor. And the Tea Time Talks will be incorporated into the Interpor Academy as the Young Academy. So this is happening from the next talk on. So we are going to start with this special edition of the Norwegian chapter of Interpor that happens on the 15th of June. So we are skipping the session that would be scheduled for the 1st of June. That will be 2 weeks from now. We've been trying to keep consistently 2-week intervals between the talks of the Tea Time Talks. We're skipping that one because on that week, we will be all focused on Interpor. That is the Interpor week. And then the first session just after that will be the formal starting of the Interpor Young Academy Tea Time Talk. So thank you very much once again. Thank you to our speakers, not only the ones from today, but all the almost 40 speakers that we had in this first year of activity. I'm very happy to see that it's been going so well. And together with the whole team here, I would like to thank you. And we'll see you at Interpor 2 weeks from now and at the first session of the Young Academy Porous Media Tea Time Talks on the 15th of June. So bye-bye.